In our next topic, we would like to show you how to use infinite limits to prove bounds between any two functions. In fact, there is a connection between the big O, big omega, and big theta concept between any two functions and limits. So the question is how to find bounds, upper bound or lower bounds between any two functions. There are two common ways of proving bounds between two functions. The first is according to the basic definitions of each of these notations. The second, which is much easier approach, uses infinite limits. The limit theorem states that if you have two functions f of n and g of n, now if you take limit for f of n over g of n when n goes to infinity, and if the answer is equal to a, then based on the answer of a, we can conclude the following. If the infinite limit goes to 0, then what does it mean? It means that g of n is larger than f of n. So when n goes to infinity, g of n will grow faster. So its value will be greater than f of n, so therefore the answer is equal to 0. And based on that, we can conclude that f of n belongs to big O of g of n. But when you apply limit between any two functions and you get the answer 0 and prove that f of n belongs to big O of g of n, also this proves that f of n does not belong to big theta of g of n. And if it does not belong to big theta of g of n, then it does not belong to big omega of g of n. So it looks like it is from left to right. If a function belongs to big O of another function, then that other function does not belong to big O of the first function. So you cannot go on both directions. If the limit is equal to infinity, then that means f of n is larger than g of n. So when n goes to infinity, f of n will grow faster. This is why the answer for the infinite limit it's equal to infinity. Then what can you conclude? You can conclude that f of n belongs to big omega of g of n. At the same time, this proves that f of n does not belong to big theta of g of n. Additionally, we can say that f of n does not belong to big O of g of n because it does not belong to big theta of g of n. Finally, if the infinite limit is equal to a finite number but other than 0, then we can say that f of n and g of n grows with the same rate. So no function is larger than the other function. And this can be defined as an asymptotic notation by f of n belongs to big theta of g of n. And since f of n belongs to big theta of g of n, then it belongs to big O of g of n and belongs to big omega of g of n. Here I would like to have a remark. Let's go for example on f of n belongs to big O of g of n. Here we said that the infinite limit equal to 0 because g of n grows faster than f of n. So if I look at the relation or the asymptotic notation from f of n, then we can say f of n belongs to big O of g of n. And if I look at the asymptotic notation from g of n, we say that g of n belongs to big omega of f of n. Similarly, when the infinite limit is equal to infinity, then that means f of n is larger than g of n. Then as an asymptotic notation, I can look at it from f by saying f of n belongs to big omega of g of n. And if I look at it from g of n, we said that g of n belongs to big O of f of n. For infinite limit, there is a theorem that will be useful for us to use it for proving bounds between two functions. This theorem is called L'Hopital's rule. It says if you have two functions f of x and g of x and they are differentiable functions, and if both infinite limit of these functions is equal to 0 or equal to infinity, then if you want to find the infinite limit for f of x over g of x, it will be equal to infinite limit of derivative of f of x over derivative of g of x. To apply this rule on some functions that are commonly appear in the analysis of algorithms, we need to review the derivative of these functions. Assume that c is a constant and u and v are differentiable functions of x and n as a rational number. The first derivative is of a constant, and the derivative of a constant is equal to 0. Second is the derivative of a function raised to power n. It is equal to n multiplied by this function raised to power n minus 1 multiplied by the derivative of this function. The derivative of len of any function is equal to the derivative of this function divided by the function. Now the exponential function, if e is raised to power a function, then the derivative is equal to e raised to power this function multiplied by the derivative of this function. Now log is similar to len, except that the base are different. This is log of a base a and this is base e. So the derivative of log a of any function is equal to the derivative of this function divided by len a multiplied by this function. Now if we have a constant a raised to power a function, then the derivative is equal to len a multiplied by this constant raised to power this function multiplied by the derivative of the function. Now the derivative of the sum or difference between two functions is equal to the sum and difference between their individual derivatives. Now the derivative for a multiplication of two functions. First, you multiply the derivative of the first function by the second function plus the first function multiplied by the derivative of the second function. And finally, the derivative for a function over a function, it's equal to the second function multiplied by the derivative of the first function minus the first function multiplied by the derivative of the second function divided by the second function square. Before giving you examples on how to use limits to find bounds of functions, we want you to know that this method can only be applied to find the bounds between two functions. And if you want to find, for example, big O, big omega, or big theta of a single function, then you need to use their basic definitions. So let us solve some questions now on how to use limits to find bounds between two functions.